There is. It's all on video. All right. Are you with us? Logger Pro. All right, let's do Logger Pro.
I'm opening it up right now.
Come on, we're 5 minutes into class. We should be rolling here.
No, we're.
Okay, it's open.
Nancy, why don't you just sit here with me?
Well, I know. He wants this big one.
The button, the blue and the red, that's the best.
All right. So, if you remember, we plotted the points for this gentleman throwing the ball. All right. And also we had some notes. So also get out that note paper that you had with all of the graphs on it.
Always get to sit next to me.
Excuse me, slide.
All right, so eyes up here while you're getting that out. Let's talk about projectile motion. All right, there's a couple of things that we discussed about projectile motion. Now, ladies, at this point, I know you really want to get caught up, but it's more important that you just listen, okay? And then when we have a little bit of downtime, then you can, okay? So just resist the temptation. Everybody talk to me. What are some of the things that we have learned about projectile motion? About maybe the vertical and the horizontal motion. Horizontal is constant.
The velocity in the y direction has nothing to do with the velocity in the x direction.
The velocity in the y direction has nothing to do with the velocity in the x direction. Okay? So we said the horizontal velocity Vx naught equals Vx. It's the same thing. Vx naught, Vx naught, Vx naught, Vx naught, Vx naught, Vx. It's always the same. V naught. Always the same thing. What about the vertical velocity? Is that always the same thing? No. What happens with vertical velocity?
It gets smaller as it keeps going up, and then it starts decreasing.
Yeah, it gets smaller as it goes up, and then eventually hits 0. So at the very top, the velocity in the y direction is 0, and then it starts going downward. Okay, so velocity in the y direction changes. What about acceleration? Is there any acceleration horizontally?
Yeah.
No.
Acceleration in the x
Oh.
direction?
No.
Nope.
Vertical.
What about acceleration in the y direction?
Yes.
Yes.
Negative 9.8.
Negative 9.8 meters per second squared. We could also talk about the initial coordinate, this point right here. It has an x naught, and we could also talk about its original coordinate, y naught, just because that's its initial x and y value, x naught, y naught. We also, if you zoomed in on this section right here, you said you've got initial velocity vector v at angle theta. You've got Vx naught and Vy naught. Does anybody on their paper have a value for Vy naught? We did trig ratios with these, and we said you can always find the vertical component of the velocity. We use, does anybody know what this is? Ivan, you got it on your paper?
Sine.
Sine was involved.
Oh, okay. V sine of theta.
V sine theta. Vx naught is, I should say V naught. V naught cosine theta. Okay? And then we talked about some graphs. All right, we had the, I'll tell you what we can do. Put them all right here.
Sin was y, correct?
sine.
Sine.
Sine is y, yeah. Y naught equals v naught sine theta. And then we talked about some different graphs. And the reason I'm saying all this is because we didn't get to the very most interesting point of it all, and that's something called the parametric equations, okay? So we definitely have to get there. Oh, it really is. You have no idea. So this is the x position with respect to time, the velocity in the x with respect to time, the acceleration in the x with respect to time, the y with respect to time, velocity in the y with respect to time, and acceleration of y with respect to time. Pick a graph, any of those 6 graphs, and tell me what they look like. Those of you that were here on Friday. Miranda, I see you looking at me. Which one of those graphs do you want to tell me what they look like?
Vx and time is a straight line.
Straight line. It's always going to be whatever that initial velocity was. Agreed. Kevin, I heard you start to say something. Pick another one of those 6 graphs.
Vx not, or Vx.
Done.
No
Sorry,
acceleration.
that's the one that
Or
you just showed.
AX. I mean.
Acceleration in the
yeah,
x direction.
there's no
Great.
acceleration.
It's what now?
There's none, so it's like on 0.
It's always 0. Okay, great. Y'all took care of some of those nice ones. Somebody else. AY is constant. What is it? Negative 9.8. Run out of the easy options. Somebody else. What about velocity in the y direction?
Decreasing.
What's that?
Decreasing.
It's decreasing. Keep going.
It starts positive.
Starts positive. Goes down like that. This corresponds to this value, high velocity in the y direction. Then it gets smaller and smaller. Eventually it goes down to 0, and then starts going negative as the object falls down. Okay. Now we're getting a little bit more interesting. What about the x position with respect to time?
Going positive.
Well, it starts off at 0. If we declare that as the origin, after 1 second it's here, after 2 seconds it's here, after 3 seconds it's here, after 4 seconds it's here.
Yeah, it'd be going up, starting like that.
Starting at the origin, and it's a straight line like that. Absolutely, I agree. What about the y
It would
position?
be a parabola, wouldn't it?
Yeah.
It would be, and that's where we ended, because if you think about the y value, it starts off here, this y value is here, then it gets a little bit less, then a little bit less, then eventually it's 0, then it comes back down like that. So it starts off at 0. So 6 different graphs, wow, that's great for parabolic motion. And what we did on Friday is we isolated each one of those over here, and then we used the curve fitting techniques that Logger Pro offers in order to graph that. Are we rolling? Okay, good. So I think that should answer all of the questions if you're looking at the lab, okay? The equation of the ball's x position with respect to time. So that was this one. Equation of the ball's x velocity, the value of the ball's x acceleration, equation of y, equation of velocity with respect to y, and then the ball's y acceleration. Okay. So then, we don't need to carry all of these graphs over to Google Sheets, but it looks like we need to do 1 or 2 of them, I guess. I don't know. Let's see what it says. Use Google Sheets to make a graph that traces the ball's position over time. So, I think I know what we're going to do. We're going to make a graph that is none of those graphs.
Another graph.
Another graph. The most interesting graph. Okay? This graph. This graph is the ball's x position and y position. So it's here, then it was here, then it was here, then it was here, then it was here. Redrawing it maybe a little bit cleaner here, okay? This is just its x versus y. Or I should say y versus x, but anyway. We'll just call it its position graph. We're gonna see with a given x, where was it? In other words, we're going to recreate, go back to Logger Pro real quick. it's essentially this graph right here. Okay? Because what you were doing is you were plotting the points, this x at that y, this x at that y, this x at that y. You all see what I'm saying? And so time is not really on this graph. At least the graph of those dots. You'll notice, and hopefully, that this parabola does resemble this parabola, but notice the difference. What's the difference between what we're seeing over there on his picture and this right here? It's the time here that we're going to see. All right, so here's what we're going to do. Go over to your data. No, there should be a data over here. I don't see all the numbers. You know,
Maybe we make it
Make your
smaller.
picture smaller.
go to page, maybe.
His picture's covered up.
Oh, go to page. Try page. Go to auto arrange down there. Oh, there's the data. Can we make this a little bit larger?
Could I delete this one? This is the instruction.
Sure, you can just delete that. Yeah, or pull it out. There you go. Okay, so Kevin and everybody else, what you're going to do is we're really only interested in this column of data, the X column, and the Y column, okay? So if you want to copy those, or if you want to copy all of it and then delete everything else, whatever you want to do, that's fine. I think you might be able to, yeah, sure. So we're going to copy that.
Google Sheets?
Yep, we're going to go to Google Sheets. And paste those values in there, and we're going to make a scatter plot, and we're going to find the equation.
Do we need time to, or just X and Y?
Just X and Y.
Did you get time? This is not three things.
We're gonna make a scatter plot. Just the X and the Y. Yep, just the X and Y, because that's what we're going to be plotting. So now, Kevin, you can literally delete the time. I don't care about the time there.
Oh.
If you right click on the right there, you should be able to delete the entire column. Sure. There you go. You want to try just to leave this as is and just see if we can insert a chart?
You
See
said
if-
delete the time?
Yeah, we don't need the time because we've only got two axes here. We don't have three-dimensional graphs yet. All right. So we just want the X. We're gonna have Y on the Y-axis. We're gonna have X on the X-axis.
Oh, that's not it.
Well, that was okay, but we want to change that. Well, okay. That was fine. We're gonna. So if y'all forgot how to graph, okay, where did you go? Let's just go to Insert,
Okay, there, I got it.
and then we're gonna go down to Chart. Now this is not really what we want. We're changing the chart type down to Scatter. Always Scatter because we have a bunch of points. There we go. Now doesn't that kind of look like the guy in what he drew?
Mm-hmm. Yeah.
Because it left his hand, it went up, and then it came back down. Looks great. Let's go ahead and let's label some things here. So chart axis and title. So chart title, Y versus X. Sure, that's actually not a bad title because it has Y versus X. We don't need subtitle. Let's go to horizontal axis. Yep. Label it X. That's good, but then always, now this is a key sticking point here. Give it the units. All right, so meters. It was in meters, so we'll put meters right there. And then we'll change the vertical axis. It says Y, also in meters. All right, everything's looking pretty good. The only thing that I want now, since he has a graph that looks like this, I want to figure out what's that equation. So then maybe if I'm going to use this equation to, I don't know, maybe I'm going to model an animation or something like that based on this. So we want to go to see if we can find that trend line. Where are we looking here? All right, hold on. Kevin, you're doing it faster. So you went to series, hit the arrow, clicked on trend line. Uh-oh, not linear, right? That trend line looks pretty bad. Let's change that. What do you think it's going to be, Kevin? Polynomial is correct. Specifically, a polynomial of degree 2. That means quadratic. If you remember your polynomials, you've got quadratics, cubics, quartics, quintics, so on and so forth. 2 refers to that exponent. It's going to be an x squared. Okay.
So change the color so you can't really see it there.
Yeah, sure. Change the line color to like red or something like that. And wow, and look at that. I don't know about y'all's, but his is, I mean, this almost looks like a string of beads, okay? That doesn't happen all the time. In this case, we've got some really good data that lines up. Okay, you'd make it all sorts fancy. Can we scroll down any more, Kevin? Can we show the r squared value? Yeah, I want to see that.
Oh, that's close.
All right.
It's because of this one.
Trend line for y, r squared value is 0.99. That means you got 1. That's even better. Can we show the equation? Let's look at the label right here. Use equation. Right there, okay. Click on that. Alright, so where it says label, we want to say show equation. In which case now we should have something like, he's got 2.5 plus 1.59x plus negative 0.499x squared. Not necessarily what I would call standard form, but we can modify that. Okay? So I'm gonna write that in standard notation. That looks like negative 0.499 is approximately 0.5. So 0.5x squared plus 1.59x, and he has plus 2.5.
Shouldn't we have relatively the same data?
Yes.
My equation's a lot different.
Did you go all the way to the bounce?
I saw right before.
Okay. What's your leading coefficient?
5.57. Wait, what do you mean? How am I
I've rearranged this.
The x squared part.
Yeah, I put the x squared term first.
It's negative 0.0117 x squared.
Okay. What's your y-intercept?
5.6.
Interesting.
I might have called you for.
You know.
Check.
Anybody else get a number more like Kevin with a negative 0.5? Those of you that remember algebra 2, I'm not saying that's all of you, but you may remember this. All right. What sort of shape is that? What do we call that thing? Parabola. Now y'all remember anything about parabolas? You know, you have a leading coefficient here. This one is negative. Do you remember what that means about your parabola? Yeah, it opens downward. Hey, what do you know? It does. I already hinted at this part. This number that stands alone, okay?
It's the y-intercept.
That's the y-intercept, because when x is 0, then this term is 0, this term is 0, and so we have 2.5. That's why I said that was the y-intercept, 2.5 meters. That sounds about reasonable for the point that you let the ball go. That's, you know, somewhere up there, roughly. So yeah, that looks pretty good. All right, now what we're going to do, since you all have your calculators, let's go ahead and graph it.
The r squared part also, or no?
No, the r squared is extra data. It's metadata about this. Kevin? The r squared tells you how close this matches with those dots. Because it's not exact. Those dots are not 100%, you know, exactly on that line. Let's go ahead and now don't graph Kevin's equation unless you haven't gotten that far yet. Graph your equation.
Except my inch-wide stuff, just because my origin is probably more.
Okay, that's fine. Depending on where you're, Gracie, that's a point that might be different. Where you put your origin,
I put it as ball.
Okay, mine didn't great.
that's gonna be then. Okay, so
Like it's where the ball was still in hand.
so basically, so this whole thing is shifted up.
Okay.
It's like your origin is gonna.
Is that okay?
Yeah, because your graph would look like that, but obviously it's gonna be a different equation.
Okay.
Oh, sorry.
That would make sense.
For the, sorry, for the x, isn't it supposed to be plus 1.59x?
Probably. I don't know. What does it say on your thing here? Plus. Yeah, it is plus.
I think this is squared. Sorry, friend.
All right, once you get that graph, just go ahead and show me what that looks like. Does it look like what you?
No. Like that.
Why doesn't it? It does. Sure. You just use scale.
Plus.
You good?
0.011.
Just graph it.
Okay.
Yeah.
That's a good question.
Oh, una grapa.
No, no es una grapa.
¿Es una grapa?
What's the R
Shoot out
short
some.
¿Qué
I
grapa?
said it was like extra.
Close enough.
Probably anything.
Yeah, because English is my second language. But
Me too. That's
English,
my
oh.
gráfico.
Literally.
Yeah, that makes more sense.
Now don't put the R squared part. Yeah, 2.54 plus 1.599. Yours almost matches his exactly.
La gráfica, el arte gráfico.
Not yet. I want you to do around here for this next part. Okay. Y'all graphed it? Graphed it? Okay. Yeah. Well, does it match your graph there?
Yeah. I think I don't know if the values are right.
Why is your? I'm looking at your Y values. Look at your Y values. That ball's going up 15 meters.
And that's why I don't know.
Something doesn't feel right. Did you label that as 2 meters?
No, it was
Did you
more.
label that as, this whole thing is
I
2?
thought it was one.
Okay. All right. Possibly. All right. So far, so good.
Oh yeah, that changed things.
All right, get out your piece of paper. We're gonna do some. We're gonna knock this up a notch here. All right, horizontally. So add this onto your handwritten notes because this is something that is not in the lab. We'll get back to the lab here, but this is what the lab is. One thing I wanted to teach y'all. Okay, here's a question. Can we find an equation for the x as a function of time? In other words, can we find x of t equals something, something, something? And then we're going to do the same thing for vertical. Can we find an equation for x as a function of time? So where we can figure out what is the x position based on a given time. Now, you already said, some of y'all, horizontally. Talk to me about that motion, horizontally. Constant velocity. Agreed. So it's here, then here, then here, then here, then here. Okay? So, we've got constant velocity. What is that velocity? Kevin, we're gonna have to go back to Logger Pro in order for us to figure out what is your constant velocity. let's go. How are we gonna find the velocity here from this shot? There's a couple different ways. I'm open to suggestions.
I want to see velocity.
Oh, X velocity. Okay, sure. Let's look at that. Yeah. I mean, whoa.
That it was spread out. I think the sections were too.
Yeah, we had. Okay, that's pretty good. Do you want to find an average value? I mean, I'm looking at right around. You want to say 3?
Oh, what? Oh.
Double click on one of those numbers. Just double click on one of them. You can double click on either right click or auto scale. I think we want to change to auto scale. We don't want the auto scale. Auto scale from 0. Try that.
Oh.
And hit OK. Okay, so now we've got 0. All right. What do y'all want to say for this? We'll just pick. We'll all have the same value. Okay. His is it'd be nice if we could figure out what the average is here, don't you think? There's got to be a way. Kevin, select all that. So let's see if we can figure out the average of this thing. However, are there any of these things that show like statistics or something like that?
Wouldn't you just take the X velocity and everything and add them all together and divide them by the numbers?
Add up all of those points.
Yeah, from your data and just divide them.
You could just do that. Let's look at this one. Let's say data collection. What does that one do? I don't think that's what we want. I'm looking for something that's just going to give us a nice little report. Is there anything that says statistics up there? I don't like that. Okay. Is there any other way that we can find the velocity, average velocity, except we just want to eyeball it? Does anybody know how we could find the velocity?
The line of best fit.
The slope of what graph? Which graph though? The velocity is the slope of the x position graph. Okay, so let's do that. So let's go to the x position.
That's not pretty.
Just X.
Yeah, just x. Let's grab that and let's find the slope. So select all of it. Okay. Let's just click and drag all the way across. There we go. It's okay if you only select like 90% of them, okay? And then we're going to go up here for the line of best fit here. There you go, x equals mt plus b. Hey, they've even given us the whole formula right here.
So nice of them.
Well, you know what? I'm going to just forget about, what is that formula? X equals, read it off to me, Kevin. Well,
X equals mt plus b.
okay, mt plus b, okay, obviously. Now, what is m for you?
3.093.
3.093 times, is that right?
Yeah.
Plus b?
Negative 0.449.
Negative 0.449. So everybody write that on your paper. X of t is 3.093 t plus negative 0.49. I'm just going to put minus 0.449. And now, Kevin, y of t, didn't we already do this and we figure out the...
Yes.
Yeah, okay, so we'll all just write down Kevin's equation here, so that way we can all do this. We're going to get a pair of equations. Both of them are going to depend on time. All right? So, Kevin, go over to your y right there. Let's find the equation of that. Remember, this was the quadratic one, I think? That's cubic.
Oh.
There you go. Tri-fit. 0.999 correlation. Looks good. We're all going to use Kevin's numbers here. All right, Kevin. It's obviously ax squared plus bx plus c. What's the a value?
There's two of them.
Negative 4.08 plus or minus something, because there's going to be a little bit of error. Just give me the real number. 2 digits will be fine.
Alright, negative 4.8.
Negative 4.8 or 0.48?
Negative 4.80.
Negative 4.8 x squared,
Or 0.8.
t squared, 4.08, alright, so 4.1, even better. Negative 4.1 t squared, keep going. What's B?
6.35.
6.4. T. And then for C?
1.7.
Plus 1.7.
Yes.
So we've got X as a function of time and Y as a function of time. This is another way of doing something similar, but I'm going to show you. What we can do is we can actually, with our calculator, we can plug in, we can have our calculator make a table for time, X, and Y. Where we say at time 0, it plugs in 0 to this and 0 for this and comes up with a number for X and a number for Y. Plug in 1 and it plots it. Plug in 1 for the X, or 1 for the time, figures out what that number is. 1 for the time, figures out what that number is, and it plots it. Plug in 2 for time. Plug that in, get a number, plot that point. What's that?
Are you doing that by hand? Like
No, we're not going to do that by hand. We're going to have the calculator do this. But what this is called, where you've got the X and you have the Y, and they both depend on time, okay? Where the X is now dependent on time, and the Y is dependent on time. This is something that's called parametric equations. All right, so grab your calculator and change the mode. You know, calculator on everybody does.
The functions for here.
Yeah, down there, the fourth one down where it says func, we're going to change the func to par.
And you're talking those equations. So.
And all right, func to par, and then hit your y equals, and your y equals will be different now. All right. So that's all right. We've got this. So type in 3.093, and then you're going to hit the X button. But wait, the X button has changed. It's now a T. In fact, if you look at the X button, it has X, comma T, comma theta, comma N. Minus 0.449. And then we're going to do the other one. Negative 4.1 T squared plus 6.4 T plus 1.7. I'll be walking around.
What is the graph
Func
descend?
to par.
Hey dude, I've got different graphs. Why?
Your y equals?
Why does the graph descend?
Because something's up with your y equals. It's negative 4.1 T squared.
Oh.
I have a different
Do you have
graph.
a calculator, Nancy? Go grab a calculator. It's a lab. It means everybody.
Mine does not look like yours.
T squared plus 6.
What's beautiful about that is it actually starts at time 0.
Plus
I don't.
1.7.
What do you mean?
Window's too small.
But it's a square.
I don't know how-
Negative
Wait,
4.1
window.
scale.
Zoom out.
Y max.
Oh, that does not look like a 2. That looks like a state.
That's what I've got. I have to change my window settings. Compare your y equals.
Okay.
Y equals
Jasmine, this is what it looks like.
449. Negative 6.4 is not squared.
Dang
Did you
it.
plug in your actual values?
It's
Yeah,
64.
just to make sure I was understanding.
Okay, yeah, that's cool.
Oh, it's not negative 3.1.
Sometimes I feel like
I've got that. So you need to compare exactly what your y equals to
It has to come out.
standard. All right, here we got. All right, calculator, cheers.
I did
Do
it.
you like really like that?
You get it?
Huh? No, mine's different, but I did get the table.
F1.
She looked at how we did it on her.
Yeah, go change your mode.
I don't know.
I didn't know what we were doing.
No, I don't know. That's okay. I just grabbed them and then I did the thing and then I got the
Yeah, figure it out. It's not a problem. Alright, oh, you want to see something really strange? Go to the table once you've got that.
To the table.
Isn't that kind of like what I said? That's how they yeah.
Oh, what's it's not me?
Oh yeah, that's fine. Does your table look like what I said it would look like? A
Yes.
column for the time, a column for the x, a column for the y?
Yes.
Your pre-cal teacher will eventually teach you about parametric equations, but it'll be far too late for it to make a difference for us. Okay? So there you go. See a little mark there. All right. Okay. So there you go. There's parametric equations. By the way, it is possible to derive these and figure out these just from the initial position and the velocity in the x direction. We're not going to do that at this time. But let me just tell you very quickly. It is possible, okay, to do all of this, to figure out what this formula is and to figure out what this formula is, okay, just if you know the initial position and the initial velocity, okay? I'm going to just wave my hands and say you can do that on your own. Why would this come in handy? If I didn't have, like, I wasn't maybe, didn't have all of this analysis, but I knew my initial position, and I knew the theta, and I knew the velocity, why might it be good to know, to be able to plot the x and y position as a function of time? Who would ever need to know the path that something would travel exactly?
Rocket scientists.
Okay, rockets. A little, once they get into space, yes, because when they're being propelled, then you've got a force. Okay, so that's one situation. Where else might you want to know where something would land, or where it's going to be at a certain time?
If there's a meteor.
Okay, if you know, all right. Normally that's kind of coming in, but once it enters the Earth's atmosphere, yep, it'll be in free fall and it follows projectile motion. Okay, that thing would normally kind of, it would look like this, but then it would do that. All right, keep going. What's another situation where if I knew this and this, I didn't have a picture to do the graphical analysis, but I just want to know, when is this, I want to get this object to be right here. I do the calculations up. If we fire it with this velocity, it's not going to get there. But if we fire it at this angle with this velocity, it'll get there. Missiles, okay? Or I'm thinking even dumber than missiles, because missiles normally have, being propelled the entire way. I'm thinking like, say that again?
I said rocket science.
Yeah, but I'm thinking dumber than that. I'm just thinking shells. Okay, like shells. Yeah, shooting a gun, like a big gun, like battleships. Okay, and
But doesn't that still have
cruisers.
like, so there's like rockets would because of like the whole gunpowder and like
As
all of that?
soon as the bullet leaves
the
the barrel, it's in projectile motion. Now you contrast that. Now, if you're talking about a missile or something that has propelled against, constantly, then it's no longer in projectile motion. But you can still have parametric equations, absolutely, for that. But I'm thinking more mortar shells. Okay, they've got a tube and they just sort of drop it in there and then it goes doop and it fires. All right, you can either sit around wasting 50 mortar shells, or you can actually do one calculation and then hit your target and then you can run away. All right, you can see the advantage there. Particularly when this was going on, catapults. You know the angle that the catapult's going to launch at, okay, and you know how the velocity. Then if you can adjust that launch angle, then you'll be able to get different distances and hit at different heights. So maybe, the wall is right here and you want to smash the top of the wall, okay? So you're going to have to account for that. Or maybe have it go really high or something like that. Cannons, also, believe it or not, maybe a little bit more mundane, but there's a lot of money to be made if you can understand this and then tell a computer to send something up and come back down in a realistic pattern. Has anybody ever played a game that has projectile motion? Angry Birds. Okay? People who made Angry Birds, they knew parametric equations, make it look like physics, and everybody wanted to play that game. And they've made millions, billions even actually. Okay? Alright, so the rest of the lab, you can follow along there. As far as copying the video down, doing the screenshot.
Since y'all did the equations together, our equations honestly pulled from our graphs.
Yeah, the equations that you pull from your graph will be different.
Not like ours just like do our own equations, or the equations that you show on the video. several different, to like know what's the equation.
I think I just wrote down what Jasmine had.
That's okay, did everyone write those down, or everyone?
Everyone always goes off the. Yeah, good question. All right, this will be due next Tuesday when you get back, so make sure you have, follow the rest of the instructions, take care of that on your own. All right. Also, oh, we've got another minute. Eyes up here real quick, make sure y'all know what's going on for this week on this agenda. Tomorrow, notes 3.6, have those ready for me, okay? All right, we're having a lecture on Tuesday and Wednesday. On Wednesday, you'll have notes on 3.7. Thursday, if you want to start mentally preparing yourself, we're going to have a free fall quiz. Hopefully your grade will not be in free fall after that. All right, and then Friday, when we've got that shortened class period, I'm just going to let you all, if you want to bring a ball, a soccer ball, basketball, volleyball, or some other thing, everyone's going to need to throw it and have somebody record them throwing, kicking, tossing, putting something in projectile motion, and then next week you'll come back and do the video analysis on that actual video. Yes?
What will our resources be for quiz 2D?
You will get the AP formula sheet plus 1 page front and back of your choosing. It's on freefall.
Okay.
That's everything freefall.
So we won't have a question.
All right, y'all ready to go?
Copy and paste it.